joined us. So we have our regular agenda. Usually, welcome, secretary's report, treasurer's report, membership report, then clubhouse report. Today we have the nominating committee stating who are all the next year's office bearers. Then, of course, our usual observing committee report and so forth. So just jump into our meeting. Just to start the meeting, I'll just say that thanks to those folks who put together our memorial garden at the clubhouse, Brian, Luca, and all the others who worked on it. Thank you. Then we had great star parties. Two to mention. One is in the Boston Common, where the mayor came and looked through David's scope, and she even spoke about it at one of our campaign speeches, I think. That she was so thrilled by seeing the Jupiter and such. Okay, great. Some visibility there. We also had it in Chelsea. We had several hundred people who came. In the Boston area, they got about 700 people plus. Yeah. The last one I want to mention is thanks to Marsha. She's organizing this special in this group for astrophotography. We had our last meeting on the Mondays, so once a month. So you'll be getting the emails, and the Discord group will be having chat. So having said that, that's pretty much it. So now I'll go to the first part of it. That is David Ibbett. Professor Ibbett is a composer, educator, and internationally recognized advocate for the intersection of music and science. He's a professor at the Worcester Polytechnic Institute and serves as a resident composer at the Center for Astrophysics at Howard and Smithsonian. His work blends orchestral, electronic music with themes drawn from astrophysics, space exploration, and scientific discovery. I will let you read the rest of it. He makes you hear light. That's what I think the essence of it is.
Yes.
All right, over to you. So I'll let you connect to your.
All right. Hello, everyone.
Indeed.
Met some of you before, and some new people. It's wonderful to be, here in Cambridge, Massachusetts, which is, the hub of so much exciting science. And I've been here for a few years doing these different projects, and I'm going to give kind of an introduction to this idea of science music and sonification, and then I'm going to finish by talking about this project. It's really been kind of a 3-year project, although not a billion years, about this early phase of the universe that was so inspired by kind of when I started my residency here, and the JWST is really shining a light on. So a little bit about me. I really trained as a musician first. So I did really traditional old-fashioned music degree at Cambridge, the other Cambridge. And then I went to London, this horrible sort of, mid-century grotty building. That's the Guildhall School of Music and Drama. And then this fancy, this is called The Beast, where I did my Ph.D. on multi-channel sound systems, and how they have 120 speakers installed in the concert hall to give you, that's my PhD supervisor there having a break, but they, I haven't been able to build one of these in the States yet, but if you give me $1 million, I will do it. So multi-channel sound, which is a way to increase immersion. So we'll get back to that topic. But then, none of this sort of shows the connection with science. And people ask me, how did I get so connected with science as a source of inspiration? Well, I sort of had to show you my headshot. It's kind of an old one. But there's me. That's my mother's piano, which she gave it to. She got a nicer one. It's about 100 years old. I shipped it over to the States, and it was kind of clear that I was going to be a musician from an early age. But then this cheeky chap here, that's my dad. He is a polymer scientist, a research chemist, and he was always just quietly drawing little molecules on napkins as I was growing up. And he'd take us to the lab, and he was cooking up. Have you ever had 10-cell? Nobody got anything made of 10-cell? You can get socks and pillows. His lab was working on that until he went bankrupt, but that's another story. He ended up working on biofuels. So, for the longest time I thought, well, okay, I've got to pick, am I going to do science or music and art? And of course, you can have your cake and eat it, and finding the connections has been my joy and my privilege in this funny old career. So I'm now a professor at WPI. There we go. Work with engineers, helping them write music. And I was the first guest composer at Fermilab, doing music about neutrinos. And then so happy to be here, resident composer at the CFA, doing all different. Astrophysics is such a deep well, as you know, so I've got no plans to go anywhere if they'll have me. I direct a non-profit called Multiverse Concert Series, and we do all different types of concerts on different themes, sometimes in the planetarium, sometimes at the Museum of Science. There we have an orchestra there doing Mars Symphony. We go to schools and ballet. There's so much to do. I'm proud of this one. This is earlier this year. We performed with the New England Philharmonic Orchestra. That's Black Hole Symphony. So kind of it's the scale of astrophysics really matches the scale of the orchestra in my mind. So I'm going to talk about some technical stuff now that underpins a lot of this work. This work, you've probably all heard some sonification. Who's heard of sonification? Not all of you. Okay.
In a different context.
Huh?
In a different context.
Sonification. So listening to data, often people come at it as a way to make things accessible to blind and partially sighted people. There's a lot of really pioneering work by Wanda Diaz-Merced on making astrophysics workable for people who can't see. But it's also, even if you can see, sound behaves fundamentally differently to light, especially with the way our human senses are wired up, and it can make things much clearer. Now, I show this to non-astrophysics people. I'm sure you all know. We're going to listen to probably the most famous sonification. You all know. Don't say, but have you all heard this before?
I have.
Don't. If you know, keep it. Who's not heard that before? Yeah, I think it's just a beautiful sound. Somebody who's not heard it, what does that sound like?
Aortic stenosis.
Oh, what's that? You're gonna have to. Oh, aortic stenosis. Okay, a heart murmur. Yes, I have recordings of my children's heartbeats in the womb, and it's it does. People say it drips drops of water or heart murmur, but it's of course it's two sort of stellar mass black holes merging, letting out these gravitational waves, which very, very famously were able to be detected by LIGO, Laser Interferometer Gravitational Wave Observatory. And sound just happens to be a good medium. It's not sound, it's space-time itself, but it's this continuously modulating signal that just happens to fall within the human hearing range of 20 to 20,000 hertz. Now, the black holes were bigger, the sound waves would be too low, and it wouldn't have worked. But it's just sort of happenstance that it falls within that range.
I got this tuned for.
Yes, and you get this whoop, this wonderful chirp, they call it, as the black holes spiral together. So that was about 10 years ago, and that hugely inspired me. I'll just, some of the things that I think about with sonification, because we are so attuned to sight, hearing data lets us see things anew. Sound has the ability to affect us subconsciously. Who's had a music just come on in the background and then found it's changed their mood? Right? It's part of the human experience, and we're much more filtered, I think, with our eyes. It's obviously a tool for science, but then for my part, it can be part of musical composition, storytelling through painting with sound, and also painting with data, because data tells us stories just like anything else. So I'll show you, this is kind of the first large-scale project I did, Black Hole Symphony, and it has a lot of different scenes that use sonification, and I've been sort of continued to use these techniques, and I'll show you a couple and how I end up using them in the new one. Here's a nice data set. There we go. You're all used to data. I don't have to apologize for the graph. It's a rather nice one. This was shown to me by a friend of mine early on, before we come up with the idea of doing a symphony. And it doesn't look necessarily that exciting. You can kind of see that. Have I got a laser here? Maybe. Oh yes, yes. Not a lot happening, and then whoop, something crazy goes on in the middle. And it's even more exciting when you find out that it's a relativistic jet coming from the supermassive black hole. That's the Hercules cluster, and these incredibly violent events that are flaring up in the distant universe. And if you're in the path of that, you're going to get annihilated. So it's really energetic, high energy physics. And the exciting thing is my scientist collaborator Anna Barnatska, who does work on now she's more interested in gravitational lensing. So this tells a story of what the black hole was having for lunch. And you can see that there's blobs of stuff going in and out. It's not a consistent signal, and music can help to tell that story. So this is a very simple sonification where it's a time series, and I'd say this is over 200 days. Each day becomes a musical note, and the higher the pitch, the more intense the gamma flare. So we can have a listen to that. Hopefully we've got some sound. We cranked it up.
Everything's maxed here.
So I had a lot of fun just making that melody. Well, so that's that's kind of the gift. I had some fun. I had to scale it obviously, and I put it within the Mixolydian mode, which I can talk about that more musical stuff. But then this becomes part of an orchestral score. So I'm going to play you now the finished symphony. See if you can hear this. Embedded within the orchestra, it's played by the synth and the electric guitar. There's another data set, which is the radio waves in the same time period. This is a bit from the symphony itself. At the Museum of Science in the planetarium, we occasionally get in there to do these symphony shows. Oh, there we go. This might be a sort of anticlimax there. That symphony is made of sort of lots of different scenes. I wanted to show you one more that uses a different type of sonification. This is, I love it when someone draws me something by hand.
Just so you know, people online can't see the laser.
They can't see the pointer? Oh, well, I'm pointing at the screen. I love it when it, because I'm not trained as a scientist, but I just love to learn. So occasionally somebody says, well, let me draw you a picture. Can you see, this is Anna, my friend, who I showed you before. She drew this in my studio for me a couple of years back. Can you guess what this is? What's she trying to explain to me, a non-scientist? You see the synchrotron there? The
electromagnetic spectrum.
It is the electromagnetic spectrum. Yes, originating from a quasar and the surrounding from a supermassive black hole. And Yeah, there you go. I mean, it's super complex but rich with information. And in order you need many different telescopes to capture all that data. It's full electromagnetic spectrum. We brought in another collaborator, Mojgan Azadi, who's here at the CFA. She does sort of simulations of full electromagnetic. We thought, well, this is far more than visible light. There's no way we could ever see that with the eye. But the ear has got some advantages. We can see 400 to 700 terahertz ish, which is not even one doubling. If you know in sound, what do we call a doubling of frequency? Anybody know?
Octave.
An octave, right? So we can't even see one octave of light. But anybody know how many octaves of sound we can hear? We could do a hearing test.
20 hertz to 20 hertz.
Yes, it's almost 10 octaves. If you've got really good, you should have at least 9. The 10th one you lose your 10th octave as you age. I was thinking, well, this is even more than 10 octaves. But if I use some sort of, the really interesting stuff is in here because you have all these radiating spectral lines of things that are heating up, and then it gets sort of more broad strokes at the edge. So I end up doing, I can show you my working, but I end up doing the broad line region in a very sort of one-to-one, where I take light frequencies and map them exactly to sound frequencies, and then I take the sort of full electromagnetic and do a logarithmic mapping, which, if you're curious afterwards, that's what it looks like. We take all of the light and play it on the piano, but we can actually do something a little bit experimental. You can help me. We're going to listen to this light from different areas of the black hole. You can see that different parts of the chord come from different spots. And we're going to do something a little dangerous here. Here we go. I'd like you we're going to need your phones for this. So if you'd all like to take out your phones and turn up the volume, please. And then scan that QR code. You don't have a phone? Oh. So you're all going to appear on my little app here. So this is a multi-channel sound experience, which we should have fun with. What it's going to ask you is to play a test sound to check you're getting sound on your phone. Hopefully that comes up. And then it's going to ask you where you're sitting. And I'm going to see that you're all going to pop up on my map here. You've got to make sure your sound is up for this. And when I've got a few of you, it's working, there we go. We can actually build our sonic black hole. We'll take this light, translate it to sound, and I can put different things in different places. So I'll just wait for a couple more of you. Let's see here.
So you're considered the stage.
I am the stage. Yes, yes.
All the world's a stage.
And, we usually have sort of 90% success with this. We try it, so if it doesn't work, I got 24 of you. So let's see if we can build our black hole core. There we go. I've got 26. I think that's pretty good. All right, here we go. So we're going to start on the edge, which is the galaxy, the sort of the lower infrared.
Are we supposed to test the audio?
Yeah, well, it should work if your volume is up now. Okay. So that is the sort of ambient light from stars. If we move further in, so people in the middle of the room will get the dust torus. There we go. And then even closer to the middle, we're going to get the broad line clouds, the superheated gas. And you can hear that high sort of squeaky gate sort of a sound. That's the ion line making this Doppler shift. It's moving up and down. We've also got a couple of gamma jets. Let's have a jet over there. Oh, is it that right? No. Sorry, I'm reversed. Yeah, that's right. A jet over there, and have another jet kind of at the back. All right, so now put your phones down on a chair or on the ground, and let's explore the black hole together. See if you can find some different things. Come on, I want to find. So in the middle, just put your phone down. Oh, see if you can find. If you listen to this note, that's the dust torus, which is about here-ish, kind of in a ring. We've got a jet. We've got some jet right there. There we go. That's the gamma rays. What have we got over here? We've got the galaxy over here.
I think you do need to put the test on there.
We've got the event horizon about there. We've got the jet just there. That one. Some high frequencies. Different things for different places. I'm so sorry. Yeah, let me know if it doesn't work. Me and my students built this, so it's not 100%.
That's pretty cool.
Yeah, I know, once I did continue, it's
It came over and started getting turned around.
I wasn't aware there was a minute.
Once you push the button,
Yeah, once you say continue, it goes away.
Oh, really?
Yeah.
What, do you have an Android or iPhone?
What?
Do you have Android?
This is the
No,
iPhone.
it's the iPhone.
iPhone.
When he pushed the test
As
button
soon
on
as
mine,
you did continue,
It freaked out?
it went down.
Okay. Well, we'll get the logs, we'll figure out.
Okay.
We've done this with about
During the
300,
test mode, it
300.
was working.
And we never get 100%. All right, time to silence that black hole. There we go. My student Wilson Kramer helped me build that. Thank you. Thank you. And, yeah, a lot of fun. So maybe I don't need $1 million to build a 100 channel set. I just need 100 phones, and I'm good. The low frequencies aren't so good. All right, so those are some of the techniques that I've developed, and I'm sort of in the throes of writing this symphony about the first billion years of the universe. And it is so rich with data and theory and new observations coming in from JWST. I will say that this symphony is dedicated to Lisa Cooley, who inspired me, and I've been working. It's been about a 3-year project. It's gone through various iterations. And the final project will be a movie at the Museum of Science that you can kind of on their planetarium running kind of every week, and then
You have a list of dates when you're playing at the planetarium?
as soon as I know, it's going to be either late this year or early next year. We start.
Did you send it to the club?
Absolutely. So a lot happens in that first billion-year period, obviously, but it's actually not the very beginning. We start at the cosmic microwave background, that point of recombination where we go to the first neutral atoms. Yes?
I was going to say, if you have the first couple of seconds, I'll give you the Nobel Prize.
No, I think that, no, it's less than that, right? Well, inflation is what, a tiny fraction?
Oh,
It's like,
it's a 10 to the minus 13th.
the part we don't know is even smaller than that. I think we're good on the second as well. I do want to write a Big Bang symphony, but that one that will come later. So actually, it's starting from so recombination is 380,000. And we've built quite a team to put this together. There we go, dedicated Lisa. We're embarrassed of her. There's a lot of people who've been helping me with this. And of course, it starts with, you've all seen this. This is the cosmic microwave backgrounds. And you've probably seen it. You can listen to the original signal that Bell Labs were picking up. They were listening. They thought, is our antenna broken? They shot the pigeons, and that still didn't fix it. you know, it turned out to be the earliest light in the universe. But you may not have heard. Coming out there. Of course, it is extremely random. The order, the patterns within the signal are, you know, within a fraction of a sense. But I've been learning a lot of the theory of this, and you can get what's called a power spectrum by analyzing the signal, and you get these acoustical peaks, which, you know, started off on an incredibly small scale, but perhaps caused by inflation. That's the leading theory, but we don't quite have the evidence on that, so that's what I'm told. And the structure of these peaks, the amplitudes of them, and the distances between them tells us about our universe and what it's made up of, the amount of matter, the amount of dark matter, dark energy. So it's, you know, it's this very important signal, and you know, we can see this is sort of what different, if our universe were different, the power spectrum would be different. And you know, here's the one that we live in, and if I take the ratios of these peaks, I can do my thing and I can get some music out of it, and you get these rather lovely relationships. You know, as a physicist I spoke to some years ago, Matt Claiborne at NYU, he was saying, well, you know, it should just be a perfect harmonic series, you know, an octave and a fifth and a fourth and a major third and a minor third, but it's not. It's this funny contorted, you know, you get slightly more than an octave there, then a fifth, then a fourth, major third, another major third. It's you know, it's a little bit inharmonic. So this is kind of my seed for the new symphony. And here's what that sounds like. A little bit bright, that's because of my piano, but also a little bit mysterious. So, you know, I was sort of hooked as soon as I heard that. I chose this A. That's my decision. But then everything else is the ratios coming from the sky. And then what else can we do with this signal? Well, I've been learning that it just because it started off very small, now it's grown very big. This light. You can see it in the CMB, but you can also see it in baryonic acoustic oscillations. This wonderful, maybe that should be my band name. But what used to be very small is now the distances between galaxies. And you know, people at the CFA are measuring this and sort of showing those peaks on the largest possible scale. And I can create a metaphor for that with music. Anybody know what happens if I take a musical harmony and I slow it? If I take a harmony and I slow it down a lot, pitch drops. What happens when it goes below human hearing?
Infrasound. So you feel infrasound.
You feel it. You do. It becomes a rhythm.
Sure.
Harmony and rhythm are in fact the same thing. An octave is 2 to 1, and a perfect fifth is 3 to 2. So let's do that with my chord. There, right? So that's our cosmic rhythm. Those are our baryonic acoustic oscillations. I can make that a bit clearer if I do a little bit of rounding. We can play those rhythms. I'm just looking at the time. I want to make sure I get to a couple of these things. So I'll probably skip this bit. This is another ingredient, is what the first star what the first star might have been like, and it probably just had the Balmer series of spectral lines, and I can play those on the piano. And then what might a very metal poor star, a sort of second generation star, have been like. This was at one point the most metal poor star discovered by Anna Fragel. It's been beaten a couple of times since then, but you'll hear that I have a real piano in this piece, and then a piano that's playing these lines of stars. So let me play you a little bit of kind of the first movement of this new symphony, arranged for a small ensemble, so it's a pre-orchestral, performed in this room, in fact, about a year ago.
Of this chaotic coalescence, the first star shines. Massive in size and burning with a flame of pure hydrogen, the chimes of our orchestra play its light spectrum as musical notes as the electrons dance in their shells around blazing hydrogen atoms. How long can such a massive furnace sustain its radiance?
So that was the death of the first star, or supernova there. I've got just a couple of minutes. I want to show you. This is what I'm working on this week, and it's sort of stressing me out, but hopefully it'll all come out in the wash. So the symphony starts off with just the light, and then dark matter halos forming the first star. We then get sort of early reionization of the universe, these little pockets of charge, but then it doesn't coalesce until we get the first galaxies and the first supermassive black holes, which are, as far as our current understanding, you need these anchors to form these galactic structures. And I want to see, can I take this these different galaxies, which are, the JWST is pushing back the earliest galaxy we've seen, but then there are these different galactic features that we want to know. When is the first disk? When's the first rotation?
Sure.
So there's kind of a story of galaxies that we've seen them one by one in the last movement of the symphony. And can I make some galactic melodies? So I do a kind of image sonification with these, where they have such curious shapes, and I know some of it is happenstance, that what the telescope is able to resolve, and the particular angle we're looking at. So this is an important galaxy, GN-Z11, because it's the first supermassive black hole that we've been able to detect. And so the melody, we imagine we're sort of traveling around the outside, kind of a clock scan, and that generates a melody. We get a higher pitch if we're further from the center, further from the core. So you'll see what instruments I chose to play this one. So that's GN-Z11. A little bit later, we see this guy. This is Max 1149 JD1, just JD1 for short. This one is special. Z9.11. A little bit closer to the present day, still within that first billion-year period. And it's got inner rotation, Hubble and ALMA. So I use it's a smoother shape that might be just with the resolution. This is played by the cellos. We've got this fun one, Revels 25, rotating disc, and it's got these wonderful puffy bilious clouds. This one is on the winds. Ooh. And the last one here, this is a gigantic elliptical galaxy, huge, much more massive than we expected to find. This is JWST, much bigger, much more evolved than we thought was out there. And this is on the strings, full string section. They're quite chaotic melodies, aren't they? I've had some fun with sort of scaling them, but I tried to let the galaxies speak for themselves. Here's what they look like written down. Musicians are going to have to play these, so wish them luck. Here they are all together. Just writes the music for me, which is really the joy of doing this. So there we go. That was sort of yesterday. So I'm in the thick of it, and I think was that 5 minutes?
No. I wasn't timing you, but I just can't help thinking of the movie E.T. where they were playing the music and.
Oh, you mean Close Encounters?
Yeah, that one.
Absolutely. Well, maybe we'll beam this out. Wish me luck. So over the next few weeks, I'm going to try and finish this piece. Thank you very much for having me. And next show is in this room on June 6th. Come and see Chemistry in the Universe. Oh, we have a question.
Yeah. Have you considered doing variable stars?
Would love to. I mean, there's there are many of them, and you can basically find one going at pretty much any frequency you want.
CH Cygni has 3 separate periodicities.
Ooh.
And it'd be very.
I could do all 3.
one of
Yeah,
my favorite stars.
Absolutely, and I love the history of that as well with Henrietta Levitz.
Look up CH Cygni on the AVSO website.
Okay.
And
Yeah.
look at the pattern. You'll be very impressed.
It's full of the music is out there. We just have to find it. Yes.
Neutron stars.
Yeah. I just finished a piece about the Crab Nebula pulsar, which is it's within audible range, just about. It's a very low B flat, so that one will be coming out. That's part of a Chandra project. Yes.
I have a question. When we look at the visual picture, the image, should we be thinking of it as edge on or face towards us?
For which one?
For the music matching the image.
For the galaxy.
For the galaxy.
So it's I'm imagining. I guess we're sort of traversing. So the further the outer edge is from the center, the higher.
So this way then.
Yeah, the higher. It gets higher as we go further away, further extended. You could have done it the other way around. We don't have sort of standardized rules, and I'm trying to find the music. I should try it the other way around. There's a UN report on sonification. It might be useful if we could all just agree to map things the same way, but we don't.
All right, so.
Thank you very much.
Thank you.
Yeah.
So, Professor Lisa Cooley will present Oxygen, the Breathing the Universe. She also serves as director of the Smithsonian Astrophysical Observatory, director of Harvard College Observatory, and professor of astrophysics in Harvard's Department of Astronomy. In this fascinating talk, guests will follow the story of oxygen from its earliest creation in the young universe after the Big Bang to the oxygen we breathe on Earth today. Professor Cooley will explain how today's ground and space-based telescopes allow scientists to trace the origins and evolution of oxygen across cosmic time, and how the next generation of observations, including the Giant Magellan Telescope, will transform our understanding of oxygen on worlds beyond our solar system. Now, take a deep breath, and we are about to embark on an extraordinary cosmic journey.
All right, everybody. Today I'm going to give you a very brief introduction to the Center for Astrophysics. I know many of you are probably already familiar with it, but I just wanted to give you an update and the types of things we're doing here. And then I'll talk about the history of oxygen. That's really one of my main research areas. I did my PhD in the relationship between star formation and active supermassive black holes in the centers of merging galaxies. But as part of that, I needed to derive new theoretical models for star-forming galaxies, and we were able to predict the spectra of star-forming galaxies, and that led to the development of new diagnostics to measure the amount of oxygen in galaxies. And then we went on, and I moved from Australia to the United States. I was a CFA fellow here. It was my first real job after my PhD in astrophysics. And then I became a Hubble Fellow at the University of Hawaii. I used all the telescopes there, including Keck and Subaru, which was just fantastic. And that's really where I did a lot of this research that I'm going to talk about today, where we measured the amount of oxygen. And then finally, I'm going to move on to what we're doing now at the Center for Astrophysics and what we plan to do in the future for measuring oxygen in extrasolar planets. So the Center for Astrophysics, you're sitting here in one of the oldest parts of the building. But we are now 850 people, and we actually are spread over multiple buildings. So we occupy buildings here in Cambridge. We also have the building across the road, 160 Concord Avenue. And in Burlington, shown there, we run the Chandra X-ray Centre. And here in Cambridge Discovery Park, we have our engineering labs, and we have about 80 engineers. And we build instrumentation for the world's ground-based telescopes, as well as space telescopes and rockets, space flight systems, and we're currently doing a balloon mission as well. These are the telescopes that we use. We operate the sub-millimeter array in Hawaii in partnership with Asia Taiwan. We run the Fred Lawrence Whipple Observatory site in Arizona, and that includes the multiple mirror telescope, as well as the Veritas Gamma Ray facility, which is both submillimeter ray and the gamma ray facility are open to all astronomers around the world to use that data. We have a Greenland radio telescope, which we connect up with our submillimeter array in Hawaii, as well as a ground-based network to measure images of the black holes in our Milky Way and neighbor galaxies. And then we're also in a partnership with various other institutions, including MIT, Arizona, and Carnegie in the Magellan telescopes in Chile. And then finally, we actually started our space program just after the World War, and it was originally a solar-based rocket program, but we moved on, and we have been now building space telescopes and instrumentation for nearly 100 years. And in particular, we're very proud of our history in the X-rays. We were the institution that really developed X-ray technology for space, and we were the original principal investigators, and with our partners, then we built and launched and continuing to operate the Chandra X-ray Observatory. It's a major flagship observatory for NASA. It's still going strong, and it's a wonderful observatory. It's contributed a lot to our understanding of supermassive black holes, as well as star formation, the interstellar medium, shocks coming out of galaxies, a lot of exciting and high energy phenomena that exist in our universe. So I'm going to move on now to oxygen. We're just going to do a quick breath and breathe in. Okay, so you just breathe 0.05 to 0.1 ounce of oxygen. Maybe you do that a bit more per minute. And that means that in a year you are inhaling a ton, an actual ton of oxygen.
Wow.
That's a lot. And it would weigh about as much as a rhinoceros, if you could calculate that. And what do we do with it? So we combine it, our bodies combine the oxygen with glucose, and that creates energy. And so we breathe out the carbon dioxide, we make water, we make energy. Does anybody know what we're using most of our energy for most of the time?
What? Thinking.
Thinking, the brain. It's our brain.
Oh, 20%.
Yeah. So the other organs it's all spread out, the energy, except our brain uses 20%. So most of the time our brain uses the largest amount of the energy.
The energy is 100 watts per person, because you eat 2,000 kilocalories a day, and the brain takes up 20% of that.
Yeah. Okay. Now, what I'm going to be talking about, so this is the oxygen molecule, but I'm going to be talking about the oxygen atom. Right, all right, so now we're going to start. Big Bang, we heard about the Big Bang from David Ibbett's talk. So between 12 and 14, it's actually 13.7 billion years ago, the universe was actually only a few millimeters in size, and there was no oxygen. And then we had the Big Bang, which we see as a simultaneous appearance of space everywhere in the universe, no edge, no center. And hydrogen and helium formed, I guess what you can visualize as puddles of gas. And there was a little bit of lithium perhaps, and beryllium formed in the Big Bang, but none of the other elements. So there was no oxygen originally. But those puddles of gas collapsed in the densest clumps to form stars. The red here, this is a simulation, supercomputer simulation of the epoch of reionization. The red is the hydrogen, neutral hydrogen, and the white is the stars forming, and as they form and they ionize the gas, it becomes transparent. You start to be able to see the universe. And so that's a simulation of the epoch of reionization. We can't see it yet, but the square kilometre array that's being built in Australia, Western Australia, is going to be able to detect and map, and hopefully map in 3D what this looks like. And so that's very exciting. They're already building it at the moment. Yeah. Feel free to ask questions during the middle. We're going to cover a lot of ground in this talk. Okay, so the stars were formed in the densest clumps of gas in the universe, and this is an extremely beautiful image from James Webb, one of my favorite images. David, did you use this one for some of your? You did. I saw it earlier today.
It's a lovely melody, the clip.
Right. He uses the clip of this as a melody. It's really awesome. And okay, so in stars, there's two ways of making oxygen. So hydrogen fuses to form helium, and then fuses with another helium to form, so two heliums combine together to form beryllium. You add another helium, you get carbon, add another one, you get oxygen. And you also get oxygen through this different process in the most massive stars, so it's 1.5 times the mass of the sun. We have this CNO cycle, and so it's a cycle where you can get oxygen over here, but you already need some pre-existing carbon and nitrogen. So this is a cycle that occurs after the first generations of stars. These already need to be there. Okay, then it's thrown out of stars, and so supernova is one of the main ways that the oxygen is thrown out of the centers of stars, and also you can see it with the Chandra Space Telescope. So we can see the oxygen in the supernova being blown out of the stars. And it's actually the greenish color here is the oxygen. And you can also see in here, there's neon, magnesium, silicon, and sulfur. So Chandra is one of the only ways that we can actually see some of these heavier metals in supernova. And then the other way that we get oxygen out of the stars is through stellar winds. And so they can be more than 200 kilometers per second. These are really fierce winds, and they are blown off, particularly in the most massive stars when they enter an unstable phase after the main sequence. And so there are generations and generations and generations of stars that have created the oxygen that we have in the universe. And those are created through generations of galaxy formation. And so we say that galaxy is formed sort of, we have a tree, we have family trees here. So this is like a galaxy formation family tree. So started in the early universe with the smallest gas clumps colliding together to form larger gas clumps, and then they collided together to form small galaxies, more collisions forming larger galaxies. And you can see galaxies building up over time. And very recently, we've been able to measure the impact of galaxies, smaller galaxies falling into galaxies, because we actually can map oxygen at extremely high resolution, and we can see in some galaxies patches of extremely low oxygen where we think a dwarf galaxy that had less oxygen has fallen in. Okay, so how do we measure it? What are we doing when we're doing our observations? So we use an emission spectrum, and we take hot gas, so we're looking at the hot gas around stars, and then we're actually specifically interested in the blue part of the spectrum. And so this is an emission spectrum from what we would call a low metallicity, low amount of oxygen spectrum. And in particular, the oxygen lines that we use are the oxygen 2 line down there, that's singly ionized oxygen. It's at 3727 angstroms, and then we use the oxygen line here, the doubly ionized oxygen at 5007 angstroms. We also can use nitrogen 2, H alpha, sulfur 2, and H beta as well. We use the Balmer lines to correct for reddening from dust before we measure the oxygen. Okay, and then we look back in time and we compare the amount of oxygen at different distances from us. And so this is a very local example. This is Mimas seen against Saturn's ring, and it took about an hour for that image to reach us. But here, when we look using the Hubble Deep Field, and now most recently with the James Webb Space Telescope, it's very deep fields, we can look back around 13 billion years. So we can look at some of the earliest galaxies in the universe. We haven't yet found that what we would call the first galaxy or the first set of galaxies in the universe, but we've discovered galaxies that are so metal poor, so little amount of oxygen, the other elements, that we think they probably only had one previous burst of star formation. Okay, but we need to, they're so faint in the Hubble Deep Field that we actually can't measure the oxygen lines you just saw. So the spectrum I just showed you is a nearby galaxy. And that's a beautiful spectrum, but we can't see them like that. And in the most distant galaxies, the oxygen lines are weak for two reasons. One, they're just very, very distant. But two, if we have very little amount of oxygen, we're getting very little lines. And so the lines themselves are actually going to be weaker. And so what we use is gravitational lensing. And so this is, Einstein predicted this. And what we get with Einstein lensing is that you've got a distant target, and then the light is bent around the largest objects in the universe, most massive objects in the universe, like a galaxy cluster, and then it's creating a lens. And then that can magnify the light from the background galaxy by 10 to 50 times. And we pick the largest lenses, and so for us, those are huge galaxy clusters. Most of the mass in those is dark matter, but we're taking advantage of that to do enormous amounts of lensing. So I'm going to give you an example. So, our institution's part of the Smithsonian. So we're going to start with the Smithsonian Castle in DC, and we're going to lens it. Here we go. Now we've got a black hole, supermassive black hole in front of the Smithsonian, and this is what it does to the image. So it distorts it. So in addition to bending the towers, we have another image, a second image. It's upside down. And we also have another image of the sky in the middle, upside down. And so this is what happens, but much more complicated when we have a background galaxy behind a cluster of galaxies and it's dark matter. To be able to get back from this to the Smithsonian image, we have to do a theoretical model, and we have to model very well what that the bending of the light is. We need to know the mass and the distribution of the mass very well in order to do that accurately. And so in the past, we were able to do that for fairly simple lenses, so supermassive black holes with its surrounding material, a galaxy. But for large clusters, we had to know an enormous amount of information about where the galaxies and the dark matter is in that cluster. So we have to not only measure the galaxies and their mass, but also their velocities, so we know how much dark matter they have. We can now do that, and it's thanks to supercomputers, combination of supercomputers and very deep imaging from the Hubble Space Telescope, the Dark Energy Survey, and the James Webb Space Telescope. So astronomers have senses of humor, and in particular the naming, normal astronomy naming convention is just, letters, you all know, letters and numbers together. But I think in gravitational lensing, they tried to be a bit more, innovative or creative. And so we have different naming. So we have a Cheshire cat up there. It's quite remarkable, looks like a Cheshire cat. So the green ones are multiple images of the same galaxy bent, and the two eyes of the Cheshire cat are multiple images of the same different galaxy. There's a bullseye Einstein ring, and so we're basically spreading out the light from a galaxy into a ring there. Einstein cross, these are two multiple images. Cosmic eye along this is one galaxy that its light has been really stretched, is a different galaxy. And cosmic horseshoe, and of course the beautiful cosmic eyelash. Okay, and so this is an image of a galaxy nearby a galaxy cluster called Abell 1689, and this one has been modeled extremely well. It has lots and lots of galaxies in it, so it makes an excellent lensing cluster. And if you look closely, you can see some lensing. Can you see some lensing?
Sure.
Yeah. So there's one here. There's there. That one is. That probably is unclear. We'd have to measure that one. And there's a big one over there.
Yep.
And so there's an enormous number of lenses in this thing. We used to look at them by eye. Now we don't need to. Now we have programs that are able to do it, and AI is actually very clever at finding the lenses. Okay, then what we did was we measured the oxygen history of star-forming galaxies, and this is using lensed galaxies at the most distant that we could do at the time. So this is galaxies, so we're looking at the amount of oxygen, and the sun is at around 8.7. This is in units of log O1H plus 12. So we always measure oxygen relative to hydrogen, which was all created in the Big Bang, so it gives a good baseline. And we just add 12 to make it not negative, and so oxygen ends up 8.7. So what this means is that the oxygen actually, this is actually really a large amount of oxygen to have at 2 gigayears after the Big Bang, right? 2 billion years after the Big Bang, this is pretty high. And because this is only maybe a half solar, and was surprising, we thought maybe it'd be like this, but it shows that most of the oxygen in the universe was actually created in the first few billion years after the Big Bang, and then was only rising very, very slowly ever since.
So we don't have anything yet more deeper than 3 redshift, 3 redshift.
So the reason why I haven't shown them on here is because it's really very uncertain how you measure those. These ones are all done using those oxygen lines I showed you, but for the ones with the James Webb Space Telescope, we don't often have the same full suite of lines to measure them. And so while it does show a similar trend, there's an enormous amount of scatter. And so I want to clean it up before I would, put it on a plot and publish.
So that's essentially Hubble, which you can see with Hubble there?
Yes, and we needed to follow up. So these ones were all discovered using Hubble, and then we followed them up with ground-based telescopes. And so this was done with Keck. Most of these were with Keck.
At the top of the graph, you have mass of the star is greater than 10 to the 9th mass of the sun. Is that?
That's the stellar mass of the galaxies.
Okay.
Yeah, so we're only looking at the biggest galaxies.
Okay.
Because at this redshift, this distance, we can't detect below that.
Okay.
And so this is a way of comparing like with like.
Got it.
Okay, so that means that we discovered that oxygen was basically created here or earlier. And the first stars were formed at about 400 million years of the age of the universe. And so we're now it means that most of the elements of the universe were created extremely early. Okay, so now you might be wondering, okay, well, but what about the oxygen we're breathing right now? How did it get on Earth? So there's been a lot of work done on this recently. And so about 4.5 billion years ago, the Earth began to form in a disk around the sun. And this is an example. And actually there was no oxygen on the early atmosphere of the Earth, we think. It actually started appearing at about 1.6 to 2.5 billion years ago. How? Well, it was photosynthesis. And it was the cyanobacteria in oceans that started doing that. We still have cyanobacteria prevalent in our oceans today. And so when we talk about discovering life on other planets, it's probably going to be like this: bacteria in oceans creating oxygen through the photosynthesis. Because if you look at the history of our planet, it was only extremely recently that you've had intelligent life on the planet. The vast majority of oxygen, which is what we're now looking for in extrasolar planets and other elements responsible for life or produced by life, was created through this type of mechanism. All right, so we can see that. We know that because it's actually in the fossil records. And so this is cyanobacteria in the fossil records, and it's called stromatolites, and it can be dated. And then, so after the bacteria produced the first oxygen, there was a thing known as the oxygen catastrophe. So what happened was the oxygen reacted with methane, and that was in the atmosphere at the time, and the methane was keeping the Earth warm. And that caused the first ice age because the methane was used up. And it was actually an enormous catastrophe. In the fossil record, it looked like most of that cyanobacteria died and only a tiny amount actually survived. And that, however, because that tiny amount survived and there was no methane left to react with, the oxygen levels then rose and rose and rose. And that is what led to the enormous things that we have on our Earth. So first, before the dinosaurs, there were huge insects and reptiles, and there are records of those. This is a dragonfly fossil with 3 feet long. Yeah.
Was it also the case that the iron on Earth had to rust before we started getting iron in the?
Yeah.
Oh, iron is soluble
That's
in
right.
the oceans. Or that would be oxygen.
Yeah. And this is a millipede the size of a car. Okay, and so this is what happened with the oxygen. So it rose, we got all these huge things, and then it stabilized to around the 20% that it is today. And so, all right, so now we have the oxygen and Earth, life on Earth as we know it. Okay, so what's on the horizon for us next?
Oh my.
So next, we want to figure out the amount of oxygen on other planets, and then how did that get there? And so we want to understand, how do planetary systems form like our own? How common are rocky planets? Do any of the nearby habitable planets, so planets in the habitable zone, harbor life? Can we find signatures of life on other planets? So those are big questions in astrophysics. We have just released our decadal plan, our plan for the next decade on our website, so you can go take a look at it. And one of the main questions, we've got 5 science themes, and one of the main science themes with questions that we want to answer is, can we find signatures of life on other planets? All right, and so this is a Hubble Space Telescope image of an extrasolar planet orbit. There is an extrasolar planet there. And you can see, so if you look at it, where it changes over time. So if you map it over years, it's moving. And in particular, what we're looking for, we can now look with James Webb at the atmospheres of extrasolar planets. And if we have enough measurements, so we want to measure oxygen, ozone, water, carbon dioxide, methane, and carbon monoxide. If we know the relative amount of each of these, we can figure out whether we have an Earth-like planet, which would have all those molecules but no carbon monoxide, or an ocean-lost M dwarf. So that's a planet that could have been habitable in the past, but has now lost its oceans. And so that would have all those things, but possibly only tiny amounts or no water. There could be a carbon dioxide rich planet, so life based on carbon dioxide, M dwarf. That might probably not have methane, but would have these other things, and particularly it'd have lots of carbon dioxide and carbon monoxide. And then you could have what we call a desiccated carbon dioxide rich planet, M dwarf, which is a planet that could have harbored life in the past, but it's had too much activity, so volcanoes, earthquakes, etc., to harbor life now, no oceans. And so that won't have any carbon, any water, but it will have oxygen, ozone, carbon dioxide, and carbon monoxide. So we can now detect all these thanks to the James Webb Space Telescope. And in fact, we were one of the 4 teams that were looking at James Webb data to look for carbon dioxide in an extrasolar planet for the first time. The reason why it's 4 teams is that it was originally 1 team, but whenever you get data that you must verify and you need to prove that it can be verified and it's not just a product of your data, you usually split your team up into groups to analyze the data independently. And if they all come to the same conclusion, then you publish the result. And that's what happened here. And so this is the carbon dioxide detection from the James Webb Space Telescope data from a nearby extrasolar planet. Okay, so also, this is a spectrum, a theoretical spectrum of an Earth-like exoplanet. And so we've shown we can detect carbon dioxide. We think we have detections of methane and possibly water. These are all in the near infrared. part of the spectrum. So all of the space telescopes, James Webb Space Telescope, the next one, Nancy Grace Roman, the one after that, Habitable Worlds Observatory. So all of the next space telescopes are in the near infrared or infrared, this part of the spectrum. But where is oxygen? Down there, it's in the red. It's in the red part of the spectrum. So that is not gonna be accessible from space. And so therefore we are building an instrument called GCLEF to detect that oxygen on habitable extrasolar planets. It's going to be the only spectrograph of its type for decades. It's actually coming together in our lab at the moment in Cambridge Discovery Park. And in fact, we've built the red camera. We are bringing in the parts for the blue camera, then we'll build the blue camera. Its vacuum chamber is finished and is about to be delivered in 2 weeks. Yes?
When you're looking at O2 in the red there, is that ionized or not?
Oh, no. So this is an absorption line. Yeah, it's O2, molecular oxygen absorption. So we're looking through, so I can show you the geometry made with my hands. So the stars here, the extrasolar planets here, and we're looking glancing through its atmosphere. And it will absorb. The O2 will absorb the light from the star.
I mean, you could pick up nitrogen then too.
Possibly. There's actually hundreds of markers that we can see in a spectrum. These are only specific ones that I showed you in the previous slide. But there's hundreds of markers that we can look for.
This is a baryonic coupling or what?
I don't know that much chemistry about it.
That's what my day job is. Anyway. Okay, I just wondering.
Maybe you can tell me. All right, so we're trying to detect oxygen extrasolar planets, but we actually want to detect many elements in their atmospheres. It helps us understand what type of extrasolar planet it is and possibly maybe how old it is relative to its own stellar system's age. And we're also building 2 other instruments for the Giant Magellan Telescope, including an enormous workhorse spectrograph. And we're building a sensor system that attaches to the mirrors so they can tilt to work with this laser-guided adaptive optics system to make super sharp images. And so the Giant Magellan Telescope this is the size of it compared to some other things. So it's 65 meters. And so it's like 4 times the size of today's telescopes. And it's the footprint's actually the size of a football field. And it's around 20 stories high. This is the Magellan telescopes right now, the ones that we work with in Chile. So it's got a much larger collecting area. So it's going to actually be more powerful than a space telescope because we can't put space telescopes up that size. We can put up space telescopes with 6 or 8 meter mirrors, but that's only that big. Yeah.
We could build it on the moon.
We could build it on the moon, and we do have a program. We are looking at actively at moon telescopes, what we could do on the moon, and we've got a couple of ideas about that, and people working on that.
Great.
So
The moon would be great.
So when you're looking at oxygen with other planets, if this thing is the atmospheric oxygen, our atmospheric oxygen, the interference?
Yes. Yes, but we know what that is.
Okay.
And so we measure it also. So what we do throughout the night, we actually take we move away from the target and we look at blank sky,
Okay.
and then we subtract that off. It can change throughout the night, so you want to keep doing it throughout your observations.
Okay.
Yeah. Okay. So the Giant Magellan Telescope, in addition to looking at extrasolar planets, it's aiming to detect the first stars, the first galaxies. There's some dark matter and dark energy surveys that it intends to do, as well as I already talked about life on other planets. So right before I finish, I'm mindful of time, and I'm just on time. I think I've got 1 more minute. I want to share with you something I'm super excited about, which is that we have launched a program called STARS, which is scientists taking astronomy to rural schools. So I want to put a telescope in every rural school in America, and we are starting with Arizona. Okay, so I see astronomy as a gateway science. It's like a gateway drug, but much healthier. And it inspires kids into STEM, it inspires curiosity. So I'm an astronomer because my high school physics teacher had a telescope. And instead of doing our regular indoor physics experiments, he took us out to a week-long camping trip, which was an astronomy experiment in the Flinders Ranges in Australia. You can see the whole Milky Way. You can even see the Magellanic Clouds blacked out against the Milky Way. And what really sold me was actually seeing the moons of Jupiter. So you could see the Jupiter and then all 4 moons. And the moons looked different. Some of them were brighter than others. And every night they're in different places. And so we could measure them. We measured their orbits. And that was just like, oh, astronomy is real. And it's awesome. And so that's what, that's really what made me want to be an astronomer. And then I did a program where Rotary Club in Australia sponsors kids to do a National Science Summer School at one of the universities in Australia. And as part of that program, they had a group, which was an astronomy group called the Galileo Group, and we went up to Mount Stromlo Observatory. It was cloudy, I didn't care. There was an astronomer and he was telling us about his work in astronomy. And I don't remember what he said, but I remember thinking, I can't believe they pay people to be astronomers. I can't believe they pay people to be astronomers. And so while this program is, we don't necessarily intend to inspire kids to all become astronomers, but I do know for sure that it inspires kids into STEM, because when we hire our engineers and we hire our technologists and we go out to various places and talk about our work, lots of people come up and say, oh, I was inspired to do my career because I love astronomy, or because I really, love the night sky, or I saw a book and it had a supernova on the front, or something like that. So there is a huge need for stars. There are actually 35% of all US schools are rural, and 20% of all students in the US actually attend those rural schools. There are almost 10 million students attending the 32,000 rural schools across the US, but field trips are limited to 1 hour travel time, state rules, and so that includes visits to museums and planetariums. So they don't get to do those things, and they have the best night sky. And in Alaska, they've got night sky in the daytime, and can even do night experiments in the daytime. So what we're doing is we're partnering with Celestron, and we're giving them the 6SE telescope. It's pretty portable. It's a nice scope. Some people ask us, why are we not giving the 8SE? And it's actually heavier, and it's harder. And the teachers, they've got to carry it out, carry it in. And it's also really it's nice to set up, and then they can type in their targets, and it can slew and track, that's the hardest thing for teachers to do if they don't have an automatic telescope like that. So then for kids that are super interested in classes that get very engaged by this, we have a micro observatory set of telescopes in Arizona, and classes. This is already the most used program in classes worldwide. They propose whatever target they want to look at, and then we provide them with the data. It's CCD data, so they can do, real experiments. And this was funded by NASA to set up, and now we're continuing to run the program.
Great.
Okay, we're starting in Arizona. Why are we starting in Arizona? It's ranked 50th in the US for school funding and resources. We have our Fred Lawrence Group Observatory out there, so we've already got staff there, and we have relationships with the surrounding schools who have all volunteered to be our pilot schools for the program. So we just ran a pilot a couple of weeks ago where we brought our telescopes and the projects. We did the training for the teachers, and we asked them and the kids questions. Teachers unanimously said that they were surprised at how engaged all their kids were. We had one school where the teacher said, oh, my kids are really not, they don't get engaged in things. Don't be surprised if they're not engaged. But then the teacher said, oh, I'm really surprised how engaged they were. And this is, high school. So we're starting in Arizona. We raised $3.5 million to do all of the rural schools in Arizona. We don't know which state will be next, but we're working on various different states. So we want to encourage kids. We need more kids doing science, technology, engineering, mathematics. It's actually hard for us to hire engineers. It's really hard for us to hire electrical engineers. We need more kids doing these things in this country. So I'm going to finish up. So let's go back to oxygen. So take a deep breath. The oxygen atoms you're breathing are between 11 to 13 billion years old. Come from stars and escaped in massive explosions. And in the coming few years, we think we will discover oxygen on extrasolar planets with the GMT, mid-2030s. So a very exciting time. Thank you. Questions?
Oh, you've come to the right place. This club does a lot of outreach.
Oh, great.
Start parties in schools that can
Awesome.
actually run more than an hour.
But if you want to help us do it in Massachusetts, that'd be great.
Sure.
We will. We're doing it already.
There's a lot of synergy. I'd love to take you to lunch sometime and exchange some information.
That would be great. That'd be great.
I'm interested, it's interesting you say almost all the oxygen going early on. Was that what gamma ray does? Because supernova has been occurring right along, and every supernova gives off oxygen.
Right.
So why hasn't it increased at a continuing rate?
So we think probably there was an enormous amount of star formation in the early universe, probably because of all the galaxy collisions. We now know with James Webb that galaxies appear older than we thought they were. We thought they would appear. And that means that they've had lots of generations of star formation in the very early universe, and that would have created most of the oxygen. We're still having supernova right up to the present day, so that's why it's still marching on up and it hasn't plateaued. But very early in the universe, there must have been a lot of evolution fairly quickly in the galaxy's lifetime. Yeah.
Are the supernovas responsible for more of the non-O16 oxygen out there? Was it mostly O16 early on?
So it is mostly supernova, but stellar winds do produce some of the oxygen that we're seeing at the moment.
He's asking about the isotopes.
No,
Oh, the isotopes. Yeah, supernova is the main one.
All right.
Yeah. And and supernova also produce the iron and things heavier than the iron. Yeah.
Thank you.
Okay, thank you.
So this was Glenn's humor intro to the observers report. Here's an image taken by the Artemis II crew, 252 plus thousand miles from the Earth. Program and mission cost $94 billion. Pretty good image, right? Pretty sharp image. Next slide, please. This is a picture taken by Sal from his porch in Somerville. Go back one. There you go. Total equipment cost about $1,000.
I vote for Sal.
That's right.
That was taken with the same telescope
Six-
that our previous
The
speaker-
6SE.
Yeah, the 6SE.
I hope you all recognize this. I know Mario knows this crater. This is a wonderful crater called Clavius. It's a fantastic crater to observe a few days after first quarter moon. I hope you all get out and take a look at that. The fun part for me, the fun part of this crater isn't this string of craters right here. But if you want to test the seeing, how steady is the atmosphere? Try. Go back. Banner,
Ben, who knows how to speed this up?
I guess.
I got that.
So you want to go this? Oh, you want me to push that?
Just the top one.
Your
The
guy.
top ones for the point.
We got it.
So,
That's not my.
all right, give me a better point.
Here, you want
Well, nobody else can see.
That is the
Here.
pointer.
Here, you want this?
No. Here, see these little craters right here? See if you can see those. These little guys right here are really, really tiny. And if the seeing is really good, your telescope's got a little better, resolving capability, you should be able to see those craters. They're only a few miles across, but from, 250,000 miles away, it's a nice trick.
Anyway, thank you, Glenn, for including those slides. So question, I hear a question?
My question is Artemis 2 astronaut, the picture they took is back to the moon, right? It's not like that.
Well, they did. They saw the. Of course, they imaged the back of the moon. My favorite images are of the Oriental Basin, which I'm going to talk about more in a few minutes. But the Artemis crew saw parts of the moon that no humans had ever seen before because of the phases that the moon was in during the Apollo missions to the moon. And so the illumination was different for Artemis. They actually were able to see with their eyes parts of the far side that no other humans had ever seen before. I mean, you can go online and get maps of the far side of the moon. They're unbelievable. They're easy to find. But that's when you heard it on the news, they saw parts of the moon that nobody had ever seen before. That's what they meant. Yeah, pretty good stuff. Anyway, Planet Roundup. I want to try and keep this short because there are still snacks to be eaten. If you want to get up really early in the morning, about an hour before sunrise, Saturn is just starting to make its appearance above the eastern horizon. A pretty challenging object still at this point, but it is coming along, and time marches on. We'll catch up with that guy in the fall. Venus, of course, we all have seen it. Yes, you all have seen it in the west and in the northwest, right after sunset. It's 30 degrees away from the sun, very bright at -4th magnitude. Please try to find it in the daytime. It's so much fun. I was looking at it just the other day. It's an easy target in the daylight. You can see it in almost any finder scope you have. You just have to sort of know where to point the telescope. But do try to do some daytime observing. And the reason we're trying some daytime observing is because there are a couple events coming up at Jupiter. I've been kind of highlighting these over the last few meetings. But Jupiter's setting at about 10:50 in the evening now, as of like right now. But what's coming up that I think is cool, will be cool to look at, are two Callisto transits. Remember, Callisto's albedo is only about 20%. Dark. It's dark. So when it transits in front of the planet, it looks dark. You can see it as a silhouetted disk of the moon itself. The first time I ever saw that happening, I thought that it was a shadow.
Yeah, me too.
But I checked my app and it was like, there's no shadow. And I was like, wait, that's Callisto. So it's really cool to see. Now, the upcoming one on May 23rd starts at 6:05 in the evening. Problem, sun's still up, right? So that's why I want you to practice doing some daytime observation. See if you can find Jupiter in your finder scope in the daytime. You know relative where to look. Carefully sweep and see if you can see it. Make sure the finder's focused, right? See if you can pick it up. You'll be able to look at that in the daytime sky. Right. The next opportunity is in full daylight on June 9th. And we're running out of Jupiter season. I can't remember the exact date of solar conjunction, but it's sometime in June, late June.
Venus, I think it's June 9th.
It's conjunction June 9th with Venus.
With Venus.
But I'm talking about conjunction with the sun, where it's not visible. Yeah, nice pairing up. We'll talk about that at the next meeting. Anyway, that's what you can look forward to with Jupiter. The lunar highlight of the month, I dedicate this again to Mario. You know what struck me during the talk? If you put a telescope on the moon like they want to do, the moon won't be in the sky anymore for you.
If I look at the moon directly, okay, it hurts the eye.
I know.
I have to use a filter.
Well, they've got filters for that. Just aperture mask your scope down.
Never.
The Oriental.
The moon in the daytime.
I love it. If you've got a single element polarizing filter, you can around first quarter, last quarter, you can check out the moon in the daytime. You just sort of dial out the skylight, and you can actually observe the moon in the middle of the day. It's a very cool thing to try. But coming up in early June, the Oriental Basin, which was that bullseye crater mountain range object location they photographed from Artemis, will be visible from your backyard due to the lunar libration. During that 3 days, the lunar librations will put, if you want to see the Oriental Basin, you have to wait for the lunar libration to kind of slide the crater or the basin into view. And it'll be that way on the mornings of June 8th through the 10th. And in a telescope, you can see some of the maria that surround the basin. And here's the basin itself. silhouetted against the blackness of space, you should be able to see the basin outline as a sort of a.
There it is.
There you go. All right, do I dare touch that again?
no idea.
All right, next slide.
If you want to point, use it.
No, I just point with my finger. So a lovely double star this month is 54 Leonis. It's a nice and blue and gold star. It's relatively easy to find, relatively bright. And I would suggest, just for fun, to see a lovely blue and gold double star besides Alberio and the Winter Alberio. Check out 54 Leo. There it is.
Very nice.
Next slide. The kind of the variable star of the month combined with the nice colorful star of the month and the carbon star of the month for Joe Henry, who's out there in TV audience land. Joe Henry loves carbon stars because they're so beautifully red. And one of the reddest carbon stars in the entire sky is V Hydra. And it's a springtime object. It's relatively easy to find. Now, if you're familiar with the ghost of Jupiter right here, and you see 3242, the way I find that is I start at Alpha, that's the alpha star in Hydra. And I go down, up, down, and then I drop a little bit south, and there's the ghost of Jupiter. Yes, sir.
The human eye with the red cones has huge variability.
Yes.
It's been tested. So you might want to ask people, what color does it seem to them?
Mm-hmm.
Some people would call the same shade, because I've done that at my own telescope with at visitors, the same shade red. Others call it orange. Others call it a pale orange. The exact same scope.
Interesting.
Same moment. Different eye.
Interesting.
How big is it?
532.
Probably looks white in the 32. Jamming so much light in the eye.
You wouldn't get that with a 6-inch.
I'm just pointing out that
No, I agree.
Do
I
it
agree.
yourself. You'll see. Ask several people to tell you what the shade is. Don't tell them what color it is, and you're going to get different answers. It's very interesting.
Mm-hmm. Steve.
Yeah, and Rich, of course, the carbon stars actually look redder earlier in the evening, not when it's pitch black. Not that we ever get pitch black, but relatively speaking, right after twilight's the best time to see these carbon stars.
Joe Henry likes to point out S. Cepi. That's a lovely carbon star, but he likes to find it when the sky is still slightly blue.
Right.
And the color is even more intense. V Hydra, can I push one of the buttons to that little down button right there? So here's a closer view of V Hydra. That's new Hydra up at the top. That's Alpha Crateris over there. And V Hydra, I would go from those guys to this little asterism here, and then find V Hydra right here. And the cool thing about V Hydra, Joe likes to tell us this out in the observing field, is that it's a variable star, and it varies over a period of about 500 days. But superimposed on, this is a 50-year plot from the AAVSO website. So superimposed on these up and downs are these deep minima. Here, this one wasn't so deep, but that one. And look, see this, if I were to make believe the graphic extended out, we're heading towards another one of the deep minima of V Hydra, when it will look especially red. These stars, when they're in their minimum magnitude, tend to look the reddest. If you've ever observed R. Leporis, again, one of the reddest stars in the sky, if you can catch it when near its minimum brightness, it's remarkably red. So that's a fun star to look for, V Hydra. Check it out. Then, of course, I won't go into this. We're still waiting on this. Yeah, I know. The April challenge was M84 and 86 and other galaxies in Virgo along what's called Markarian's chain. And this is an amazing image by Mario.
Yeah,
Mario.
I'll tell you something. That was taken in Bortle 7 in Florida. And and I tried it before and couldn't get it because you lose all the other. There's a new filter put out by Antlia called RGB Ultra 2, and it eliminates the blue part of the 479 nanometers, which is what the LEDs give off. And it's to the left of it, so it's around 430 and higher. And it also is a broadband around the H alpha nitrogen and around the oxygen H beta. It gives you good color and it allows you to look at Portal 7 skies. You can use it both as a light pollution filter, luminance filter, and on a color one-shot camera like this. And I am so impressed with that. All the old filters were designed for mercury lights.
Yep.
We don't have mercury lights anymore. They're totally useless. This is the filter to get.
What's the name of the filter again?
Post that on Discuss.
Amplia RGB Ultra 2.
Can you post that on?
It's also in the newsletter, by the way.
Oh, it's in the newsletter?
Yes,
Oh,
one of the last photos we submitted.
How much is it?
197.
Cheap.
Yeah, I saw
Not
that.
bad.
Is that one and
Not
four?
bad. Well, let me click through these. This one was taken by Doug Paul. I'm just gonna go through them. All right, you guys, sorry, we're not gonna spend time. Dave-
Shot with full wideband with a 6-inch aperture, also in a Bortle 6 to 7 area.
All right, nice, very nice. Dave Murray, one of our mirror grinders. Dave's also a nice avid astro imager. Venu with a C-Star S50.
My guess is you probably bought it.
And here's another C-Star image taken by Joseph Rothschild.
8, right on the border between 8 and.
And Joe DeShane sent a set of notes. I've observed the chain with my homemade 100 millimeter binocular telescope for M84 and M86, along with the double eyes, as you see 4438 and 4435 in the chain are clearly visible. So if you've got a relatively dark sky, some of these galaxies are bright enough to be seen in a pair of 4-inch binoculars. But again, if you haven't checked these galaxies out, it's still springtime. I would encourage you to go out and find them. Play around with the Virgo cluster. Just sweep around, pick up galaxies. They're all over the place, there.
Yeah.
So have fun with that cluster. The May challenge, getting back into Leo, is the Leo triplet. It's the M6566 and NGC 3628. Easy to find, really easy to find, and fun galaxies to check out. It'd be interesting to see how many of us are able to see the 3628. Steve, that's the Hamburger galaxy, right?
Yeah.
Yeah, the Hamburger galaxy. Because
It's very faint though.
it's very thin.
Doesn't have high surface brightness. It's
Right.
tough to find.
It's tough.
Why is there red gas there in that area?
I don't know.
That's Doug's picture, Aspen.
Doug?
There's hydrogen in the region.
Presumably, but yes. Is that well known?
I don't know.
My picture.
We'll have to look into that. I can see it on the screen here too. Anyway, let's press forward. June challenge, M13 in the propeller. Now, it seems to me we just did this as a challenge, but remember, Glenn and I went back to 2009 to start the list over again. I think the propeller in M13 was literally about 10 years ago as one of the challenge objects. So M13 is a wonderful globular cluster. What's that?
You can see it right there.
I don't.
On the left side. That's the propeller.
I don't see it. Point it out.
Here.
I can see it. I can see it.
It's not the best picture, but this is it right there.
You want?
So can you use the?
Here we
Right there.
This is doing it.
Move that red thing out of the way.
That's what people online can see, because they can't see your silver point.
That, see, can you see it now?
Yeah, I can see it.
That's the propeller.
All right. So we all know where that one is. So there's no excuse. Go out and observe it. All right. I order you to observe it.
Way back 20 years ago.
The clubhouse is open in May. I guess that was last week, the 8th and 9th, but this weekend, the folks on duty, June 5th and 6th, June 12th and 13th. Come on out and join us. Look through that big telescope right there.
Next speaker is Dr. Silas Laycock, professor of astronomy. Silas. Okay, thanks for that. Silas Laycock. And he'll be speaking about the research that he does with his students and such.
Thank you.
Yeah.
And he did partner with the Sullivan ATMoB Observatory a couple of years ago with the students.
Yeah.
All right. Thanks everyone for joining the meeting. Yeah.